As the days pass on, less and less information becomes constant. Trees grow and die, volcanoes erupt, and science marches on. The few things we can rely on, however, is the ever-growing size of our node modules folder and how I will always remain on the downslope of a Dunning-Kruger graph. Let's lighten the load and actually understand the tools we use. This is From Scratch, Episode 3, Rate Limiting. Okay, rate limiting. The limiting of a rate. It's a vague umbrella term that can honestly mean a lot of things. There are, of course, times in which we may want to limit the rate of something. The way we limit this rate, however, often depends on what this something is. Let's start with a rather common use case, list filtering. I apologize for the light mode change over here. Now, I've gone ahead and imported a large data set into memory. We now have an array of user data. Each object in our array contains a name and a high score. If we want to search for a specific user's high score without knowing their name directly, we may want to perform a filter operation. I'd like to type some name within this input over here and see all the users with matching names right below it. Adding a submit button here is fine, but often not necessary. Having results change without a button press might look a lot nicer and create a better user experience. Unfortunately, doing this on a large dataset will make our interface lag, whether from the filter operation itself or from the DOM rendering. So if I type the letter D, I erase both of them, and it takes a while for it to update again. That's lag. There are some simple optimization techniques we can use to improve this, but the main one we're going to focus on is called debouncing. Alright, let's look at the code for a second. I've gone ahead and increased the size a little bit because, again, on the last video, I think it was a bit too small. Now, a debounce is a kind of rate limiting, right? Now, look at our code here first, and we're going to sort of describe what's actually happening, and so I can show the problem with our code and why it's acting the way it does. So, this is our main file. We're not going to really go into the utils folder. They're just, general files that we can use to make the process of explaining this a lot easier. We load the user data into memory. We store it in a local variable called users. We get the section container. We get the input that we want to type into it. When a user types into our input on the input event, if the user's data doesn't exist yet, we return early. If it does exist, we get their name in lowercase, and then we filter through our entire list to find the matching users within the matches array over here, and then we render those users to the screen. So in every single letter press, we're going to render all the users. Now, my computer is a little bit more powerful than most, so we're not going to have a problem with the filtering operation, but we definitely are going to have a problem with the rendering operation over here, where we're rendering a lot of content on the screen very quickly. About, I'm not sure if it's 10,000 rows in this case. And so changing that isn't great. We sort of want a debounce. I say that word a lot. What do I mean by debounce? Well, let's go to the second version, the solution to our problem. I'm using the same thing as the last time. So we see if we import debounce, and we've now debounced our function in some sense. So instead of just calling it directly, we're calling it the debounced version. So let's look at our code to see what debounce actually does. This is debounce. It's a very, very simple function, right? It's a complicated name. It's used in a lot of libraries, but it's not that complicated at its core. So, debounce is a function which takes in another function and a millisecond delay. At the top level, it stores a private variable for its own use, the timeout ID. And it returns a new function in its place. Whenever we use a rate limiting function, we're meant to have our function exist, let's say something like this, right? Where we have a function called say, which takes in a string, and it says something to the console. And then we debalance that function called say, and we store that into a new function. This comes called a debounced say. And this is the one we use instead each time. Now, of course, I keep saying this. What does debounce do? Well, the new function that it returns will clear the previous timeout and set a new timeout. What this does is it executes this function after a delay of 500 milliseconds. But if another function comes before this, much quicker, then the previous function's execution will not happen at all. It'll be deleted and overwritten with a new function. So first we're calling hello. and we wait 500 milliseconds. But before we can finish waiting, we call it with this. So we cancel the hello operation. Then we call it with is, we cancel the this operation. Then we call it with debounced, and we cancel the is operation. And finally, debounced should be the only thing that gets logged to our console. And just as a proof of concept, to show how this works, I'm going to open our console over here, paste this in, and we see I am being debounced. I am saying debounced, right? Because our function called say has I am saying and then the comma part. So I am saying debounced. This is the only part that gets logged because the previous calls got overwritten. And that's what debounce essentially does. Let's look at it one last time. We're returning a new function to the user, which they're supposed to use instead. This is the, I suppose it's the rest operator, and this is the spread operator. Not super, what they do isn't super important here. Just we're taking the arguments from the user-provided function, and we're passing it to the function that they passed us beforehand. And we clear the previous timeout, and then we set a new timeout. So we set a timeout, we're setting a delay. We're delaying the function's execution. And every single set timeout has an ID that it returns to us, which we can store in a local variable, which I call timeout ID in my case. And timeout ID is, again, local to this function, which again, each time you call this function, it will overwrite the previous one. Now let's look at the actual thing in action. So let's type out d over here, and I can erase things properly. And you'll see there's a delay. There still is going to be a delay in the rendering and execution because that's to be expected. This is a complicated operation. Debounce usually exists when we have these annoying operations that are, memory intensive in some sense. So we can type the name deb, we get all the answers, we can delete this. And yeah, again, we're still going to get a delay, but we don't get a lack of interactivity. The worst thing we can get is a non-interactive page. That's the one thing we really, really want to avoid. So the delay, can't really be avoided, but in our case, we can avoid the delay in interactivity. So now I can finish typing in the input, and then it'll render. Whereas beforehand, I couldn't even type in the input. The input itself would be delayed. Okay, and that is essentially debounce. The next one I want to tackle is going to be throttle. So let's really quickly, don't save that. Let's change our one to over here. Let's call this the scrolling problem. Okay, so again, debounce and throttle, those are the two primary ones I want to discuss here, and both of them exist to solve a very common problem, a very common issue. So let's go back to our page, and let's type out, the letter D for whatever user, and let's scroll down, right? If you scroll down really fast, you're going to get, probably should have put an epilepsy trigger warning over here, but that's what we're kind of going to get. So what does this do? What does my code do over here? I still have the debounce part over here, right? Because we're still doing debounce user input, but we've also added this over here. We're adding a scroll event to the document, and when we scroll, we're getting the scroll position. We're going to use modulus 360 because we have 360 degrees of color. HSL uses a color wheel in some sense. And based off of the current user's scroll position, we color the background. Nothing too complicated. Now, I want my users to have a very fun experience. I want them to scroll and the background changes and they'll be very impressed with my coding prowess. But again, this is too fast of a coding change. And now, throttle is a function that's used to handle continuous user input. But why can't we use debounce for this? Well, debounce, as I said beforehand, exists for input that stops at some point. Debounce you want to use for some input stream, and we can think of a lot of things like input streams of input, that has a finisher. So when you're typing something, you're eventually going to stop typing, because that's just how typing works. That's the nature of that operation. But when you have actions that deal with continuous user input, such as a scrolling operation, the user doesn't ever have to stop scrolling. So if I wanted to, I can just hold this position forever, and we're going to keep on scrolling. Right? I'm using the middle mouse button to do this, infinite scroll sort of trick. So this is an operation where we want the user to see results. We want there to be interactivity, and we want the page to change, but the user might not ever stop that operation. We want things to execute while the user is moving, and not when they finish. All right, so let's see what debounce looks like. Let's go to number 4. This is the scrolling solution. So, I said debounce, sorry, I meant throttle. Now we're importing throttle from our utils folder. We've added another thing called utils. And like the last time, we're going to wrap the event listener thing in a throttle. And we have 500 here. So what does 500 mean? With the debounce, 200 was the delay of execution. What's the window we're going to have, and within which other functions can be executed. So throttle, again, works a bit similarly. We're not that different. Like, let's look at throttle and debounce. Not a crazy difference, same kind of concept. So with throttle, we return a new function again. And this time, instead of having a set timeout, a thing over here, we're actually having a variable called isOpen. It's a Boolean this time. We're not going to have a timeout ID because we don't actually plan on canceling previous functions. Right? That's not what we have set timeout here. Instead, what we're going to do is we're going to let the user execute the function. Right? We're going to let the user call it and have it go through. But as soon as that happens, we're going to close ourselves. The lid on our function is going to be closed. We're going to lock it for a delay of however many milliseconds the user tells us to. Right? You can think of it like a button that locks itself for, like, let's say a minute. Perhaps it's an ice cream machine with free ice cream, but we don't want to have infinite ice cream coming out of it, so we allow one user to press a button, and then it locks itself for about a minute. And then it can be pressed again. So we call the function, we call the original function like this, we set isOpen to equal false, meaning next time the user calls a function, isOpen will be false and it'll return early. Then we have a set timeout to reopen the function after some delay. And that's what throttle does. Now let's see how it's actually solved our problem. Let's type D over here to have all these results. And if I go very fast, you'll see how fast I'm scrolling, but the color really isn't changing that quickly. I can scroll even faster. The rate that I'm scrolling does not affect the rate that the color changes. That is sort of the power of throttle. And we can see over here, I just added a transition, so we actually have a color fading. If I didn't have this line over here, the color would have a jarring change. So I don't really want to have that. But essentially, throttle exists for continuous streams of input, whereas debounce exists for input that ends after a while. But I don't know about you guys, but throttle and debounce have never seemed like awfully descriptive names to me. I often confuse them, and perhaps for good reason. Wikipedia even defines debounce to mean throttling execution. It's a little bit silly for a coding video, but I came up with a limerick that I think helps a fair bit. Throttle the bottle that rolls, debounce delays controls. You can replace bottle with model and rolls with scrolls. The idea is the same. You can say throttle the model that scrolls, debounce delays controls. Same idea. In essence, again, throttle is used for continuous stream of inputs, where debounce delays the input. So we can say debounce bounces it away. Maybe that will be some sort of trick for you. But again, I personally don't think the names are awfully descriptive. Now, I'm not going to end here, because debounce and throttle are the main two ones I wanted to talk about. But when messing around with debounce a fair amount, I found something kind of interesting. I'm going to first explain sort of a coding problem to show you why I find this fascinating. Now, I went a bit overkill. I made a mini sort of UI templating language. It's really a very poor man's version of this. Not very good at all. But trying to explain a certain concept that exists in modern frameworks that I thought was really fascinating. So we're importing the render function, make DOM from template, and update DOM with state. This is our state. We're going to store it inside of a map. Right? Sort of like a regular object. I just, prefer maps if we're not dealing with, objects to contain information. Over here, map is meant to be changed a lot. So I prefer this sort of hash map instead of a regular object in JavaScript. Our name is going to be Norman, and parentheses 26. 26, I guess, is how old Norman is. And so we see over here his age is 26. Emotion is happy. And this is our template. And this works a little bit like, I want to say Pug or Jade, where we have the tag at first, and then we have the name, hello, and then comma. This is a variable declaration. So hello, Norman, aged, and then 26. You seem to be happy today. Then we have a button which says increment age inside of it. Right? So this is just an easy way of creating HTML from JavaScript. And this exists for a pretty particular reason, because I want to sort of demonstrate an optimization techniques that a lot of frameworks use, which takes advantage of the concept of debounce. I thought this was really cool. This is really exciting to me. I was sort of fanboying over the concept for about a day or so. So we have an update function over here. Now the update function takes in what kind of state we want to update, and then creates a function so we can update that state based off of the previous value. And then all it does is it just updates that state, and then it renders, it reruns our template, which is the DOM object, with the new state to create a new DOM object. And then it renders that to the page with the render function. Once the page is rendered, and each time it happens, we have to do this because of the way our framework works, just because, this is how it was built. I'm sorry. We retrieve the button from the page, and then we add an event listener to it, a click listener. And whenever we click this button, we're going to change some of our state. Now, you might notice this if you've ever dealt with something like React or Vue, where you have these sort of update functions. With React specifically, we have setState. These days, we have hooks. So with setState, we sort of control this sort of global massive object. But these days, we have hooks, where we have individual state changes. And let's sort of show what this looks like. And I'll sort of try to demonstrate why this is a problem. So again, it kind of works exactly as you saw beforehand in the template. Hello Norman, age 26, you seem to be happy today. Increment age, 27, right? Nothing too crazy really happens here. Nothing too weird or insane. But I'll explain really quick why this is a very bad way of doing things. I'm updating the age, and then I'm updating the name, right? So the name over here includes the age. So whenever we increment the age, I want to also update the name. Now I could have written this in a reactive manner. In fact, I sort of did make a very thin reactive framework in my reactivity video, which was my first from scratch video. But I've made it sort of different way on purpose, sort of more like React and Preact, just to demonstrate this sort of quality or optimization that I wanted to show. So why is this bad? Well, every single time we call update, we're calling our run function, right? Every single update called re-renders our entire state. So first we update the age, and then we render. Then we update the name, and we render. So we could have a separate function, which I guess updates more than one property at a time. But let's say we don't want to. Let's say for API purposes, we'd rather create it in such that we can individually update specific state elements and have the framework somehow, magically, batch those two requests together. Now, again, I just want to show you real quick with the UI. I don't want to really focus too much on this, but a bit more about why this is really bad. Whenever we update the text with state, update DOM with state, we recursively go down every single DOM element to find out where the variable needs to be updated, right? Let's say we have age multiple times in our documents. We have to recurse down this very, very large tree. Again, if you had a reactivity-based framework, you wouldn't have to do this. You wouldn't need a virtual DOM, so to speak. But in our case, we sort of do. So we have update text with state, update DOM with state. This is a recursive function. It goes down the tree, updating all the variables. Calling it twice is a pretty expensive operation. And we're also mutating the page more than once, right? So if we re-render the entire page, I don't do it in a very beautiful looking way, but if you look at our render function, we set the elements inner HTML to be nothing, and then we append the child, which is what we generated from our DOM object. So we want to only make one singular DOM operation for more than one state update. How do we do that? Because this seems like an impossible request. What you might have is a specific batch update function. But let's talk about a really cool thing called autobatch. Right? Now I've added a new thing over here called autobatch. I've also added something called debounce keep, because this sort of plays off of the idea of a debounce. What if inside of a debounce, instead of throwing away all the functions, we kept them? So we're still going to keep the concept of executing them after a set timeout, but we're going to keep all of the calls we get, and we're going to take this arguments array, and we're going to pass that to the final function. So let's say we had our say function from earlier. So let's bring this code back just a little bit, just to demonstrate what this sort of would mean for us. We would instead of having string, we'd have strings, right? We might instead have something like this, for const string of strings, and then we have like this, right? This might be a different way we'd have to write our function over here. And debounce keep, let's use. So what this would do is only after, I guess, 500 milliseconds after the last one was called, would it log all of these together. So what a kept version of this might do All right, it's kind of confusing to know why you'd actually want to use this. Is it would execute all of them at the same time. Right, so we're kind of getting a bit close to the idea of what we're trying to talk about here. Now, what if, instead of having a 500 millisecond delay, we had a 0 millisecond delay? Right? What if that happened? Well, I guess that would technically mean that these over here would get automatically batched into the same call, because they're one after the other. A 0 millisecond delay doesn't literally mean 0 milliseconds. It won't execute directly after this function. It'll execute right after the call stack, in some sense, on the next event loop. So these would all get grouped into one sort of batch. We'd sort of automatically batch them into their own thing. And that's the concept behind autobatch. But instead of using set timeout, we're going to be using something even faster than set timeout. What could be faster than set timeout with a 0 millisecond delay? Something called Q microtask. This is autobatch. Q microtask works with microtasks. You can use microtasks with promises, which I originally built this function with, but this might be a bit more clear. A microtask executes after the call stack is completely empty, but before the next event loop. It's very quick. It's not really important how quick or the minutia of it, but we're just going to be using this for our function. So this is similar to the keep debounce method. Instead, we're going to have a current microtask exist over here and a last microtask, because we're not using set timeout. So microtask does not return to us a microtask ID, and even if it did, we couldn't cancel them. So what we're doing, a little clever trick, is setting a variable equal to the function we're creating. Right? Now we have const microtask equals, and then we call the microtask. But we have another variable called latest microtask, which you might see is kind of similar to the timeout ID variable over here. And what that means is whenever we call our function, by the time it gets executed, whenever that is, right? So before we had after 500 milliseconds, but over here it would be after the call stack is over. It'll see mi equal to this. Now, if this was the last function called, it will be equal to this. But if this was not the last function to be called, then only the last function will have itself equal to latest microtask, because everyone is manipulating this sort of shared variable. And whenever you have the last function, we call the function with all the arguments, and then we set our array's length equal to 0. If this wasn't super simple or understandable, try to pause the video, look at it, write it up yourself, and try to execute it. But in essence, if we use autobatch, right, we're importing that function now, and we have a multi-update function. So we have to rewrite it because now our function has to accept multiple parameters called updates. So now you have to have a for loop, or we batch the function somehow. And we call this batched update function over here on the bottom. And if we look in the console, I'm not sure if I added that here. I don't think I did. Oh yeah, so we have a mutating DOM thing over here, right? So if I refresh this and let's go to the console, whenever I click increment age, we see one call to mutating DOM in our console. Let's make that a bit larger so you can see that. And let's close 1, 2, 3, right? You see that over there. But if we didn't use this, if we instead used just regular old update and then save that, refreshed it, we'd see 2 calls each time, 2 separate calls. Because again, we're really running this function twice if we were using the non-batched version. So the batched version, even though we're still making 2 separate calls, allows us to batch things on the same call stack, which I thought was really, really, really cool. Now, this is originally where I wanted to end the video. But I figured it would be silly to skip over all the more common rate-limiting algorithms taught in textbooks. Debounce and throttle, as they're called in the front-end world, are the most common types in the front end. When building something like an API, however, there are more specific algorithms often at play. The main way in which front-end specific algorithms differ is that front-end algorithms are more about accepting only ever one request at a time, where debounce removes all requests except for the last one. Throttle removes all requests except for one occasionally. The algorithms I'm about to present are suited where you want to keep a specific rate of execution. We want to accept a bunch of calls, even at once, but we don't want to overwhelm our servers. That's the rate limiting we're going to talk about in a second. So let's talk about over here Let's close this, don't save. Fixed window. The fixed window algorithm. Now, I think this is the simplest one in some sort of sense, so let's first talk about that one. Now, the main way it differs is that we now have a threshold variable right over here to say how many function calls we wish to allow. Our window size is just the amount of time before our variable resets. I'm not terribly fond of our set interval here, since it's a good way to have a memory leak. I haven't provided a way to cancel it, and there may be a way to code it where we can remove it entirely, which I'll show you in a second, but for clarity's sake, I'm going to include the set interval. So, the set interval, every single time window size finishes, whatever millisecond number this is, ran functions goes back down to 0. If ran functions at any moment is over the threshold the user provided to us, don't allow their function to continue, and return false, meaning that no, we're not going to run that function. Then we're going to increment their function ++ if we actually pass through, run the function, and return true, meaning we did execute the function, it actually went through. Just real quick to show a way that we can actually code this without using the set interval, because I haven't really given a way to cancel a set interval. I'm very uneasy about having set intervals if there's a way to not have them. You can kind of just do this over here, where we have a last call variable with performance.now. This is sort of like new date, the current time. Performance.now is specific to the page. It's the, I believe, milliseconds since the page started. And we have now equal to performance.now. We do some basic calculations. Now minus last call, greater than window size, last call equals now, ran functions equals 0. Same sort of concept as beforehand. You can take a second to dissect this if you'd like. I'm not really going to go over this too in depth, but this is a way you might code this to remove the set interval and make it, perhaps a tiny bit better or more performant. So let's look at our page to see how actually this works. So we have a tasks over here. And if we can add tasks to the right, task 1, task 2, task 3, and they will get executed into the queue on our left. Now let's press this button really, really, really quickly. And we see 2 tasks over there turned red. Why is that? Let's go to our index.js file to see how our code actually looks. So I have some function in our task.js file. Again, I've sort of abstracted out the code that I don't think is super necessary to the explanation to make our main code kind of clear. It's just code in charge of updating the UI, in essence. So, this is our new rate-limited function, using the fixed window. Now, we're just going to call this over here, called function called, because it's not super necessary to me to have this function actually execute. It's going to log in the console, so you can see it there if you'd like, but I think the visual is a bit better than I have on the front end. Our window size is 1,000 milliseconds, so 1 second, essentially. 3 is our threshold. How many functions will we accept before we have to throw some away? Right, and we have, we queue a task every single time we click the button. Then we call our function to see whether it's been accepted or not. When we click that button, if it has been accepted, we accept it. If it's not, we reject it. Right, the front-end code pretty much mimics how the algorithm sort of works, and we're sort of just showing how the algorithm works. Now, you might also notice another difference from throttle. With our previous function, we would only start the timer after we called the function. Here, the timer is starting and resetting without intervention. If used in the same place, this is a really poor way of doing things, but if we assume there will be some of a constant stream of function calls, the constant timer will balance out. Right, so this is going on forever. This is going to keep going. Beforehand is a bit more clear with the set interval, but we're sort of requiring that the user have the function calls within very neat-looking intervals. But I'm honestly still not super set on this constant timer mechanic. So pretend our fixed window algorithm allows for 100 requests per minute. That's the rate we want to keep. We can imagine a circumstance where 59 seconds into a minute, we get 100 requests. Then, when the timer resets a second later, we get another 100 requests. This algorithm allows for 200 requests within 2 seconds? That's a lot higher than 100 per minute. So we try to keep sort of this interval, but we're assuming that our service is popular enough to get a constant stream of inputs. But often that's not the case. So I'm not a very big fan of our fixed window because it doesn't really work based on how rates exist. So let's take a look at another version of an API, as I call rate limiting algorithm. The next one is going to be called the sliding window. So the sliding window, we changed over here, we changed over here. We didn't really change any of the code. We don't need to. Let's go to our sliding window. Okay, this looks a bit more complicated. The sliding window algorithm realizes that the minute boundary is kind of arbitrary and a poor way of doing things, but it doesn't completely stray from the idea of a window. We can probably think of a better model, where our minute doesn't fall on a time boundary specifically, but just goes back 60 seconds until now and sees how many requests were called within that time boundary, right? Within the current minute we're dealing with. We don't need to reset on every minute, just evaluate the current 60-second window. The sliding algorithm we're going to display works a bit similarly. We don't timestamp any function calls, but we keep in memory how many requests we got within the last window when evaluating how many calls to allow for the current one. It's a bit of a compromise. So we have a function called last window, sorry, not a function, a variable, last window functions, current window functions, and then start time. Right, before we only needed this performance.now thing. In the optimized removing set interval version, over here we actually do need it always. And what we're doing is every single set interval, we're resetting what the start time is, and we're swapping the variables over here and resetting the current stuff. So this isn't too complicated. The set interval just resets our variables, it swaps them, and it resets the start time. The function we return first calculates a distance. Right, so this is a little bit complicated. We're going to go a bit slower. So performance.now minus start time. That is the current distance into how far we are into the current time interval. We divide it by the window size to see a percentage of how far we are through. Right, so if the start time over here was 500 milliseconds, we're currently at 700, and the window is 500. 700 minus 500 would be 200. 200 over 500, that'd be 2/5 or 40%. So the distance over here would be 40%. Then we get the reverse of that. So we get 60%, or 0, or 1 minus distance, comma 0, last requests, times last window functions. I'm not sure this code over here is exactly correct. I really hope it is, and I'm not just realizing I made a mistake now. That'd be kind of embarrassing. This might need to be math.max. I'm not super sure. Might need to be math. If it isn't, it should be math.max, and I apologize. Request equals last request plus current window functions. So this is the sort of calculation of how much of a percentage of the last window we should keep, right? So if we're 40% through the current window, we take 60% of the last window's functions, and we pretend to add it to our current window. Right? Again, understanding of it isn't super important over here, but the sliding window is sort of a compromise where it takes the last one and the current one. And if we look at the add tasks over here, we see that it kind of works, and it doesn't really require a time boundary specifically. Right? So I think this actually does seem to work. Hopefully I don't need to change this to math.max, but essentially the sliding window works on time boundaries, so it's still a window, but it allows us to make it work without having to have it on a specific 0 milliseconds thing. Now, again, we can also remove the set interval in this function, because again, I don't like this. It's kind of like a memory leak. If I do that, we can have it to be like this sort of big if statement. I'm not going to focus on this. I don't think it's super important, and I think it is a bit more complicated. I was originally going to explain how this worked. I don't think I should, realizing the time constraints that we have. But if you want to pause the video, this is how you might construct the function in a way to remove the set interval while still having it work as it does before. The next algorithm I want to talk about is called a token bucket. Right? This is a bit more similar to the time-stamped version I talked about beforehand. The sliding window could have been time-stamped. So the token bucket, again, this file doesn't really change. We just call token bucket. And this is really simple, in my opinion. But we have the tokens variable equaling 0. We just increment the tokens we have. And if the tokens are less than 0 at any given moment, don't let the function run. If the tokens are not less than 0, or equal to 0, then decrement the tokens and run the function. So you can think of them like Chuck E. Cheese tokens. Do you have enough tokens or money to run the function? And let's say you're running some sort of business that has passive income, right? So you're running some sort of software distribution, and you get money occasionally every 2 minutes, and you can only afford to buy some subscription or some service or some item once you have enough money. And that's sort of how this sort of emulates it. This is kind of interesting. It is in some way more exact. We ensure a certain rate by only ever allowing the total number of requests to match the total number of tokens. Each token's sort of like good for one request, and we accumulate tokens over time. Each time we get a request, we spend one token. We can also remove the need for a set interval over here. So like last time, using performance.now, and we calculate tokens based off of the performance.now, and subtracted by how many requests we've already done. This might be a clever way to remove the need for tokens. The problem with this function, in my opinion, is that it really doesn't work well to limit rates unless we again constantly get requests. If we get no requests for a while, we're running the risk of getting a ton of requests in one shot, all because we've been collecting tokens in the meantime. So let's look at our function again, and let's refresh the page. If we add it, they're all red. Let's wait a little bit. 1, 2, 3, 4, and then quickly, all those go through. So it's not really helping for rates if we have any delay, because we're going to accumulate tokens over time. And maybe you can limit the rate. Maybe you can limit the amount of tokens we get. Right? Say keep accumulating tokens unless we get to X number of tokens. But in my personal opinion, in this circumstance, I don't think it works well to mimic the architecture of the system we might be dealing with. Right? What kind of a system or architecture needs this sort of warm-up period? The new Intel processor, if you wait long enough, can do any calculation in the world extremely fast. I just don't think it's a very accurate way to model the problem. And that's what I want to get to the point of in sort of this episode. How to accurately model the problem of a need of a circumstance using a rate-limiting function. And so the last one I want to talk about over here, because I know this has been kind of long so far, I apologize, is the leaky bucket algorithm. I kind of like this one the best. This is my favorite one in some sort of weird sense, because I think it's unique enough that it can explain to us how we can vary all of our systems. So over here, you'll notice there actually is a little bit of a difference in how we write this. Before, the index.js file didn't really change. Now it did. This comment is still here. I probably should have deleted that a while ago. But we're returning a promise this time. Why a promise? That is curious. Why would that happen? Well, it's because of the way the leaky bucket algorithm works. So let's look at it. The leaky bucket. All right, this one is interesting because it has a bit more of a complex setup, but I want to mess with this code a little bit to show we can rate limit it in a custom fashion, more specific to our use case in a little bit. And JavaScript does not include a queue natively, which makes part of this a bit more complicated. We can really just use an array and the .shift method, but it's preferable to use a data structure where that operation is less expensive, where it's O of 1 instead of O of n. How our leaky bucket function works is as follows. We want to accept requests at a constant rate. That's been our, want this entire time. We might not receive them at a constant rate, however. Right? Those have been two things we're challenging. To remedy this, we save function calls for later. If we get too many of them, we throw some away. So we add them to a queue. When we get the functions, we add them to a queue. And if you know anything about data structures, you'll realize why a queue sort of makes sense. You can think of like a queue in line. We're saying, oh, you want to call? Yeah, get in line, buddy. We have some other guys. But if our queue is too long, if our line at the grocery store is going out the door, we say, hey guys, we're not accepting any more customers until this line gets shorter. I'm sorry guys, it's for your sake too. Because if we get too many customers, if we have too many people on our line, eventually one person coming to our grocery store, or whatever kind of analogy we want to use, it'll take them a few hours, and that really isn't a very pleasant experience. So we sort of want to limit our function with some sort of max size variable. And the rate over here is how often do we absorb another customer? So if you think about like a queue in a line in a store, how often can a customer's order be taken? And that is the rate. So we can pretend every 300 milliseconds, a new customer can be taken. So we have a queue, and people can come to our store at whatever rate they want to. Our line can be short for a long time. It can be long very quickly. We have a max size, so it's never going to be impossibly long. But our queue can be however long people want it to be. We'll only take customers at a constant rate, however, so that our servers can work properly. Our servers will only ever take customers at a constant rate. They're going to pop them on a set interval, which is going to be on the rate over here. If the function's length equals 0, we're going to clear ourselves. Now, we can't actually make this without a set interval. I showed you previously how we can remove this set interval in the previous functions. We can't do that here, just due to the very nature of how this works. But we can close ourselves automatically if we don't have any more people to execute on our queue. The function we return checks if the size is too large. If it is, it exits early. If it doesn't have an interval ID, then we create a new interval instead to that. That's sort of our way of saving memory, so we don't have this interval going unnecessarily. Now we're returning a promise, because I think this is a nicer way to make this API work. You don't have to. That's just what I thought might be a clever way to notify the user when their function got executed. We're returning a promise, and inside of the promise, we're pushing the res function, along with the arguments that the user provided to us. This is going to be on our queue, so when we pop an item from the queue, we get an args, and we get the res. We call the function with the arguments, and we pass that to the resolver of the promise. This promise will now be resolved. So this is a clever way of having this promise be resolved within this set interval. I was able to cross boundaries by, inside of the promise's callback function, essentially push it to our queue outside of this. Let's see this work in action. So let's add a task. We had a bunch of them. This does not seem to be working. Why is that? I believe I may have messed something up over here. In some sense, return false. Return push. Index.js is accepted. Let's check my console. Some last second debugging. QJS function called to 0. I did not want to do last second debugging here. This was not how I planned for this video to end, right at the end of it. To avoid taking too much time over here, I probably don't want to debug this on stream. And I'll essentially just sort of take the easy way out and say this is essentially the idea of what we want to get. If it didn't actually work in the end of the day, there's probably something wrong with a small part of my implementation, not the overall problem, because I've gotten this to work in the writing session, in the practice. Now, I like the leaky bucket algorithm a lot because it's a really interesting way of doing things with a queue. And I think the queue, having it mimic the architecture of your system, is an interesting way to describe how you might have a rate limiting function. Because you can have rate limiting functions that don't exactly mimic this architecture. An interesting function that I might make was maybe called async buckets. Let's make a new thing called async bucket.js, and let's say export async bucket, right? This is one that I came up with where we use asynchronicity to run functions. So the function will be run, again, we have a certain bucket size, or max size over here, and we have a current list of running functions. We increment the thing, and then we await the function, see how long it takes to go. So maybe your rate limiting is very input-output heavy, very I/O heavy, and that means that an asynchronous fashion, an asynchronous rate limiter might be pretty important to you. Now, this does not ensure that they get executed in order, right? Some guys' function could be executed sooner than another one's, but the same, again, idea of having a rate limiting function match your architecture of the problem is a very smart way of doing things. Don't just pull out a debounce or a throttle. Understand your problem. Understand what the best application is for your specific circumstance. And with that, I want to say thank you for watching. It's been a bit, but I appreciate you for sticking around if you have for this long. Till next time, stay curious.